Hey guys, welcome to the Real Hacker Hours podcast. This is just where I do the work on side projects that I normally would do, but I just hit the record button before I do it. Today I will be reversing the Sqlite3 insertion process. What I mean by that is like when you're inserting a new record, what exactly happens under the hood. Without further ado, let's get started. This is also what I do when I do this work, is kind of just explain what I'm doing as I'm doing it. So here we have a GDB session with Sqlite3. We run it. We're going to open up a database. We're going to run one query first. That way we actually load the database file into memory. Cool. Now next we are going to set a breakpoint for a particular spot. This spot is effectively, actually let me show you the source code where it is. What is this function? The function that executes the actual SQLite opcodes is here. So let's go there. Yeah, SQLite, when it actually runs the operations to service the query, it does so via opcodes that are executed in a custom VM. This is the function that actually handles that. And this is a switch statement where you can see like case, op go sub, op init coroutine, and it's basically just a switch statement that will service the various opcodes. And what this line right here, what it kind of correlates to, or these few lines of assembly code basically correlate to this line right here. So I set the breakpoint for here. What I'm going to do, my ultimate objective for this next step is I want to capture all of the opcodes associated with the insertion process. That way we know all of the effectively the code that is ran to actually generate and insert a new record. So let's just do a query. Actually, I'm going to type it out here because it's easier. Insert into X, Y, Z values. Let's go 10, 1, 1, 1, 1, 1. And hopefully I remembered what the database schema is. Actually, oh wait, I forgot to actually set the breakpoint. It just, yeah, smooth brain mistake. Just check. Okay, now the breakpoint is actually set. Let's go there. So now I'm just going to quickly just record all of the opcodes as we see them. 3E, RAX, yeah, cool. So we have OX3E, which corresponds to 62. All right, our opcode list. Yeah. Okay, cool. So the first one is 62. And by the way, the reason why it's RAX comes from this portion right here. Next is 2, so let's jot that down. 11, OX62, which is 98. 98 again. 4x45, 69. OX74. So we have 116. By the way, yeah, if you see the monitors flicker, that's because I have like 2 of them and I just switch back and forth between them. So next up, OX7A. It might be nice if I could just whip up some nice GDB scripting just to handle this for me, but I'm a pleb. OX5B. So 091. OX4E 78. OX4F. OX5C. OX5C. OX85. OX. No, so it's a 7B. 7B is 123. How nice. OX44. I think this is halt, so if my memory serves me right, this should be the last opcode that is ran. That is the last opcode. Cool. Let's match all of these opcode values to what the corresponding opcode is. This right here is a list of all of the opcodes that are generated with this source code file. I believe that this is established in like Sqlite3.c. If it's not there, just in some other source code file that's generated at compile time, if I recall correctly. 62 is op init, which that's good. That's the opcode that we should expect to be ran first, since when it starts generating like VDBE code, it's always the first one that is appended. Next is 2, which is op transaction. So let's get that. 11. Go to, yeah. These are typically the 3 opcodes I've seen out basically at the start of all operations, I should say. Open rate. Cool. Open rate again, since it's that twice. 69. Integer. One 6. String 8. New row ID. 91. Affinity. Actually, let's copy. And then next is op and copy. Make record is called twice. IDX insert, okay. And then we have that, and then finally we have halt. Okay, cool. So these are the opcodes that are used. Now, one thing that I'm pretty sure, even though I forget the exact specifics of this particular database, I'm pretty sure that we're using an index with this one. The reason for it being is I see that there's 2 open writes and effectively 2 inserts and 2 make records. And I'm pretty sure that corresponds with, from my experience, that corresponds exactly with indexes, since when it tries to run queries on a table that has an index associated with it, it will both deal with the table itself and an index. Also, just to backtrack, effectively what an index is it's a separate data structure that's made to store additional metadata about the table itself to increase query speeds, if that makes sense. For this particular reversing, I don't want to deal with if I don't want to deal with having indexes, so I'm just going to effectively just remake the database real quick and then go through this process again. Let's go here, run dot open insert. Let's just quickly create table x y int z int. No, let's do a varchar. And select all from x, insert to x. Right now, I'm just typing out some of the SQL queries that I would like to use to run queries in the database. Insert into x columns y and z values 0, 1, 2, 3, 4, 5. Okay, now let's set the breakpoint for where the opcodes are generated, which happens here. Okay, we have this. Let's set that breakpoint, continue. Now let's rerun this insertion query. Okay, yeah, I'm going to go through the same process as I did before. I'm just going to like pause the recording real quick so I don't bore you guys too much with this part. BRB. I'll resume it right after I finish it. Okay, so I am back. Yeah, these are the opcodes that I ran as part of the insertion of a new... of inserting a new record, op init transaction, go to open right integer string, make new row D, make record insert halt. So briefly looking at these opcodes, I can like tell you like at a high level what they're doing. These three are the three opcodes that are ran at the start of every transaction. Open and write. This opens the table so that we can actually write to it. What these next three opcodes are doing is they're preparing the three, effectively the three different values that are going to go into the record. As you recall from the previous, the SQL query I ran, there was integer and a string. Op integer prepare the integer value, string prepares a string value. The new row ID would it would prepare the row ID associated with that record. Now, because I don't have a primary key associated with the table, this functionality is handled under the hood. It really isn't shown to me. Make record, that actually constructs the record. Insert is what I will actually insert the record into the table. Now, here, let's start taking a look at some of them. Case op. Let's look at the integer. Okay, so this just sets a register equal to P1. Okay, what the op integer and op string is, okay, taking a step back, with the VDBE virtual machine implementation that Sqlite has, it has its own version of, actually I need to, hang on a second. Okay, yeah, so, yeah, these three opcodes, effectively integer, string, and new row ID, they're configuring the three values of the new record. Let's take a quick look at the case op new row ID. Get an integer number. Okay, let's just... So effectively, the code for that is this right here. Let's just copy and paste it into a new tab so you can look at it. nicely. Where does it store? So it's stored in a register P2. Let's do Control F for P2. P out V. Okay, let's just take a quick look through this code to see what it does. So I believe this is getting the, this is moving the cursor to the, okay, actually, v equals 0. Okay, so looking at here, what this right here is doing, this right here is a check to see is it using a random row ID. If not, what it will do is this moves it to the last record, which if the table is using row IDs that increment, like first record has ID of 0, second record has ID of 1, third record has ID of 2, the last record should have the highest ID value associated with that record, so it moves to that. Then it will effectively, this right here gets the value of that record, stores in V, increments V by 1, which is then set equal to the output. So that P3 is a valid memory. This right here, okay, this right here appears to just be a check for the validity of the memory cell, and this right here appears to check, is how it generates the row ID if it's a random. Sqlite3 randomness. Okay, cool. So I'm not going to spend too much time looking at this. So effectively from here we can see that for our case it's going to be using this. Just moves the cursor to the last record of the B tree, which, assuming it has incremental row IDs, should have the largest. Gets the value of the row ID and just increments it by 1. Cool, so we understand that. Let's take a quick look at op open right, which is this op right here. Didn't spend too much time looking at that, so you go to op open right. Okay, we can see here that the code for this is also the code for open read, and it appears that the code for the op reopen IDX also runs into here. Let's look in the comments. We can see the values open. So open a read write cursor to the table. Okay, so looking at these comments, it appears that like this opcode is just responsible for opening a read or write cursor to the table. We could probably have guessed that from simply just going off the name of the opcode. However, let's look through this to see what it's doing. In this case, creates the cursor using to the B tree. By the way, one thing you might be seeing B tree around here a lot. The reason for that being is how it models tables using B trees, and the reason I believe for that being is you won't see this functionality so much with like a vanilla table that I have. However, when it starts getting to indexes and starts getting to like the dealing with efficiently searching through a database, that's when the B tree functionality really comes in handy. But yeah, Sqlite3 tries to model its tables after B trees. That's where we're seeing like B tree cursor, B tree insert, that sort of stuff. So as you can see, it creates the cursor there. Open cursor, break, right. Okay, yeah, and yeah, right. WR flag. Okay, yeah. Okay, so yeah, so effectively, looking at this, it appears that the majority of the functionality for actually opening up the right cursor to the table or the B tree is done with the Sqlite3 B tree cursor. Just gonna save this. Okay, so now opens a right cursor to the table, prepares the 3 values for the record. Let's take a look at the make record opcode. So you go to case op make record. Okay, cool. Let's copy this over into a separate tag because I get the feeling we're going to be spending a bit of time with this. Okay, cool. So let's first look at the comments so we can understand what like the parameters to this should be. Convert P2 registers beginning with P1, the record format, into a database record in a database table or a key in an index. Okay, cool. So the amount of registers is stored in P2, but the records are actually start with P1, then go to P3, P4, and there's an arbitrary, like printf, there's an arbitrary amount of arguments to this opcode, but it's effectively just trying to generate the record. Okay, so let's start looking through here. Apply the request. Yeah, also, one thing I should probably go over, this is what a record looks like. There's a header side, there's a record header, and then the record values. It starts off with a header size, which is the size of the header in bytes, then the data types for that, then it has actual data. Before this, you will also see like 2 metadata values, like one of which is like the ID of the record, which is typically like 1 or something, and the second, I believe, also is like the actual size. If you want, I could open up a hex editor and show you, but that'll be later. I know I'm about to like release some like memory documentation, like explaining this stuff. Now, looking through this further, apply the requested affinity to all inputs. Loop through the elements. So, this is a do while. Okay, do while. What is this doing? Okay, so effectively what this loop is trying to do, like, judging from this comment, is it's just trying to determine how much space is needed for the record. With that knowledge, let's see, there's a few if-then statements that are occurred. If what is set equal to? Okay, so right here it's grabbing it appears to be grabbing like the value of an the register value. Let's Okay, yeah. Actually, let me... Okay, yeah. So we can see here, this appears to be grabbing the else if actually. Is there another if? Okay. So yeah, taking a step back, this loop determines how much space is in what belongs to or is required to make the record. What you have here is you have a series of if-then statements that determine like roughly like what the type of data it is. This if-then statement deals with integers. We can see that from this if-then statement here. Now, looking at how it does it, this grabs the value right there, and then what it does is it proceeds to do a series of if-then checks. Now, the reason why it's checking these values, if we go over to Python, let's get this value right here, copy it. We see that it's OX7FFF. Let's try this right here. 7. What it's effectively trying to do is it's trying to determine, can this be stored by a 2-byte integer? Can this be stored by 4-byte integer? This is probably 8 bytes. Actually, got that wrong. And 2. Oh wait, yeah. One thing I just realized that I'm 1, 2. Okay, I just realized something that I was making a smooth brain mistake. You can clearly tell that it's 2 bytes by the fact that it's adding 2 bytes of additional data to that. So if it's less than or if this value is less than or equal to this value, we can store it as a 2-byte int. If it's less than or equal to that value, store it as a 3-byte int. Less than or equal to this value, store it as a 4-byte. If it's less than or equal to this, store it as a 6-byte integer. One thing that I just saw that's a bit interesting, prect, I'm not sure what this is. For all of these, it's set 2, 2, 3, 3, 4, 4. For some reason, 6 and 5. Let's see what that is later. And if it doesn't meet all of those, throw it as an 8-byte value. Okay, where does this end? Here. Okay. One thing I'm going to be checking for later on is like where prec is used exactly. So next we have this. I'm a memorial. Not too sure what this is. It looks like it's kind of a generic catch-all. Actually, not a generic catch-all since else is right after that. Looking at the next block, let's see. Serial type. Oh, okay, I can tell. What this is doing right here is it's calculating this final one is for in the event that it has a string length or the data type is a string of some sort. With integers like a 2-byte integer will always be able to be stored within 2 bytes. A string can be 1 byte, it can be 50 bytes, it can be 500 bytes. So it has to actually calculate it. The formula it uses is the length times 2 plus 12. And also how it differentiates between text and blobs is like if one's odd or one's even. That's the reason for the ×2. Okay, cool. So yeah, what this loop is doing, calculating the size of it. This code right here calculates it for an integer. This code right here calculates it for strings. Cool. Moving on. Purec. Oh, okay. Interestingly enough, what does Purec initially plast? Infield. So infield is initially set to register value of 2 of register P2, which, as we saw earlier, should hold the value for the number of columns going into this record, number of values going into this record. Data plast equals. Okay, so plast is the last record in here. We see prec is set equal to plast, so it's calculating it from the last record forward. And we see here that it moves back. Prec is kind of like the current value that's being inserted into the record, and it's iterating from the last value to the first record. Not the first record, the first value. And we see here something else. If this in header, what is in header set equal to? In header, okay, looks like this header plus plus. Oh, okay. In header looks like this number of bytes needed for the header. Now we see for the integers, it's just incremented by 1. Reason for that being is since there's only like 10 different types of integers, specifying if it's like a 0 byte, or not a 0, like a, well, that's just null, like a 1 byte, 2 byte, 3 byte, 6 byte, 8 byte. You can have all of that designated by a single byte, whereas due to the extreme increase in entropy with the sizes for strings, you might need multiple bytes to store that data. That's why for integers it's just incremented by 1, whereas for strings we see it's actually not just, it might be more than a single byte. Okay, so we see that if it's less than or equal to 126, it adds 1. And var it equals. Okay, cool. So looking at this, it appears that there's, oh yeah, the header begins with a var int that resembles, yeah, it begins with a value that is the size of the header, and that's what this block of code is taking into account. Effectively, what this check is can that value be stored with a 1 byte value? It can. Okay, just increment it by 1. It cannot. Okay, then increment it by a variable amount. Cool. And then it calculates the size of the total record by adding the amount of bytes for the data to the amount of bytes of the header. And let's just, what value is being used for these? In byte. What is, so one thing to take note of. So in data is a U64, and header is an int, and byte is an I64. So it's 3 separate data types. Okay, that might cause an issue, it might not. Let's see. Because like sometimes when you add like a signed integer to an unsigned integer, like you can have some weird behavior that happens, since like -1 can be negative numbers can be interpreted as really large unsigned integers. So probably won't be able to do anything with that, but I'll have to check later. So let's make sure the output register has a buffer large enough to store the new record. Let's be the one. Else. Byte plus 0. Okay, cool. So yeah, it's checking if the output space designated by appears the P3 register is big enough, and if not, it calls this function to handle it. Also, we see here something interesting. It appears that there is an actual like limit to how big a record can be designated by. Actually, yeah. Okay, looking further ahead, we see few more checks. Okay, this loop right here is where it actually will create the record. Does so by prec. Okay, yeah. This time it just iterates from the first value to the last, and effectively just it will put the header value in the header, and then use this to put the data value in the data section. Cool. So we briefly went over and we have a rough understanding of how it makes a record. Let's look at how it inserts a record. So you go to case op insert. Let's copy this to. If I recall correctly from, I know when I reversed out the like memory allocation schema, I think I've looked at this before. Yeah, the majority of the insertion logic will take place in Sqlite3 btree insert, which we'll call where is it? I remember looking at this before, so I'm kind of going off of that right now. Let's copy this to a new tab. Btree insert. No. Remember there being a function called I might be wrong, but I remember there being a function. Oh yeah, insert cell. That's what it was. Insert cell. This function here, I believe, is where it actually gets inserted, if I recall correctly. Insert cell. Void. Okay, and yeah, effectively what it will do is it will allocate the space using this function and then do a memcopy call to it. And what allocate space will do, it allocate space. How does it do it? Effectively, I know this from, I just got done reversing memory. Actually, that's a specific function. Actually, let's look at it so I can explain it. It is integer. So, there are effectively 3 different spots that it can find, or 3 different methods for it to actually allocate space. The first way is there's an actual free list associated on the page, and if it can find a spot for it to store there, it will. Second method is, as part of the metadata for the page, it stores the amount of like fragmented bytes left over the page, and if it sees that, hey, there's enough fragmented bytes in order to actually store this new record, it will defragment the page, and then this last one, which the defragmentation runs into, is where it simply just allocates space from the free section of the page. And one more thing. Insert cell. One thing that's a bit Sqlite3 B tree. Insert. And also just to like prove that I'm not. We can see here, let's IB delete 1 breakout insert cell, just to prove that actually like will run the insert cell function. We can run this and then breakout allocate space. Oh wait, I believe allocate space. Let me just make sure I got the spelling right. It might be inline, which is the reason why GDB doesn't see that. I did see that a lot when I'm reversing this, is that it would just inline certain functions, so they don't actually exist as their own standalone function. B tree. No. So, oh wait, I think B tree. Sir. Yeah, it didn't actually. Oh wait, insert cell. Allocate space. Let's just make sure I got the spelling right. Yeah, it got inlined, and I'll show you here. Just gonna step for a while until we approach that. Okay, note that you can see right here where we are approaching the allocate space. Yeah, right now we're at it. Note that the assembly, that we're not going to actually hit a call before we actually jump into the code for that. Yeah, we've entered the code for allocate space, which we can see here. Let's Control F for this. Yeah, we're in the allocate space function. However, we can see that when we made that jump there wasn't a call instruction. So yeah, it just got inlined into that function. So yeah, just to recap, let's look at where are those opcodes? So yeah, from what you've seen, these 3 opcodes are just appended to the start of every action. Open right, that gives us the cursor, which the cursor is just like what allows us to effectively browse through the table. It gives us the cursor in write mode. These 3 values just prepare the 3 values for the record. This actually constructs the record as you saw. This one will insert it into the table, and this just halts the operation. since this has gone on for 45 minutes, I'm gonna cut it off here, and we've effectively reversed the insertion process. See you guys next time.